All right, so I started the recording for class. Just a reminder, homework number 4 is due tonight. Okay, so if you go into the classroom, under homeworks, homework number 4 is due tonight. How many people, hopefully, how many people have started it? I know it's your shortest homework of the class so far. All right, so I got one person started. I'll take questions on it in a second. Yeah, I'll take questions. If anybody has questions, I'll take questions in a second. But if you haven't started with it, it shouldn't take you too long. And you definitely just have to have it in by 11:59 tonight. All right. I've also posted your homework number 5. And this homework number 5 is due Thursday the 8th. Ignore this due date here. My apologies from that. Okay, there's a little bit of a typo. That's wrong. But it's due Thursday the 8th. And you're able today, after class today, you're going to be able to do questions 1, questions 2, and you should be able to do question number 3. And then question number 4 we'll do next class. We'll talk about question number 4 next class. And then you'll also be able to do question number 5 as well. So you'll be able to do after class today every question but question number 4. Okay. So that's due Thursday the 8th. Also on Thursday the 8th is your next exam. So next Thursday. The homework is designed to get you ready for the exam. And so I'll do a review on the 6th. So real simple review for the exam. I've also posted some sample exams. If you go back into the classroom and look under week 11, I've posted some sample exams and some extra practice problems. So if anybody wants some extra problems to tackle, you can download them there, and you can even ask me questions in class on them. And then after that, like we're in the home stretch. You know, I feel like we have like 6 weeks of class left or something like that. Yeah, where is it? Yeah. So it's kind of crazy. All right. So homework number 4. Before I get started, does anybody have any questions on it, or want to see me do any of the problems, anything like that? For those who did the homework already, was it pretty straightforward if you use the calculator? Yeah. All right, good. Yeah, it shouldn't be bad. So this is the type of stuff that's going to be on your exam coming up. So if you found this homework pretty easy, the table. Yep, that's okay. The table's a little. Going forward in the class, we're just going to use the calculator whenever we can. Every once in a while, we'll load up the statistical table and look at it again, but then I'll always just show you to the calculator. We'll always go to the calculator. Being a remote class, I want to rely on technology as much as we can to help us. I hope that's okay. All right. Any homework questions before I jump into today's lecture? Any questions in general about anything? Of which question? 1C, question 1C. All right, so let me load up my graphing calculator for this. Okay, so it says this is 1C here. Suppose talk time. I'm sorry. Did I cut somebody off? Nope. Okay. So it goes like this. Suppose that the talk time on an iPhone 8 is normally distributed with a mean of 12 hours and standard deviation of 2.5 hours. Okay. So we know this is what we know for the homework problem. Talk time is normally distributed with an average of 12 hours and standard deviation of 2.5 hours. So then part C says, if an iPhone 8 is selected at random, what is the probability its talk time is between 10 hours and 15 hours? All right, so we want to find the probability talk time is between 10 and 15 hours. Okay, so the first thing you do is you define a variable. Okay, you say, I'm going to let the random variable x be the talk time on a randomly selected what's it? Did I say iPhone 8 or 10? I forgot here. iPhone 8. And then I want to find the probability that x is between 10 and 15 hours. All right, I know it seems silly, and unfortunately, you're going to hear me say this a bunch. But what do I find really helps me solve these problems? Besides the calculator. What do I always say to do?
Draw it out.
Yeah, I like the drawing. Draw it out, okay? So you're going to draw the distribution of talk time. Okay, follows this bell curve, whoop, the probability distribution for it. It's centered at 12, and I want to be, for whatever reason, between 10 and 15. Okay. So the easiest option in your calculator is this thing called normal CDF. And you have to input 4 things into the normal CDF, okay? You need to input, you need to input a lower value, then an upper value, then the mean, and then the standard deviation. All right, so for this problem, what is the lower value I'm interested in here? Where does the probability start? Yep. So I'm going to go 10, comma, and then where am I going to go to? Yep. And then it's the mean, which is 12, and then the standard deviation, which is 2.5. So it's literally, you just go second function, distribution, normal CDF, 10, comma 15, comma 12, comma 2.5. And that's your answer right there. It's 0.6731 when I round it. And that's it. Maybe like the hard part is sometimes figuring out like what to put in the lower and upper, but once you figure that out, like the calculator just goes doot, 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 and just does it for you. Yeah. All right. Everybody else pretty good? Ready for a fun and interesting lecture today?
Yeah, let's do it.
One person. Yeah. All right. So today kind of begins the study of, no, I won't take off on that. Julia, no, I won't. And on your exam, I build in a tolerance that it accepts a range of values. So if you round incorrectly, or if you solve with the table instead of the calculator, it'll accept both answers. I'm not a stickler. Do professors like take off if you round a digit wrong? Like that just seems crazy. Unless it's a question on rounding. Wow. Okay. Jeez. I yeah, I don't know what to say to that. Yikes. Well, I'm giving you a break, so there'll be that. Okay. I mean, maybe in chemistry it's important. I don't know. Exact values are important, but for this class, I'm more interested in the analysis and the steps than you rounding correctly to 4 digits. Not the biggest deal. Okay. You guys are welcome. I know it's remote. Nothing's easy anymore. So you got to go a little bit easier every once in a while. Okay. So this begins a kind of like the advanced study of statistics. Okay. So this begins our advanced, I'll put in quotation, study of statistics. So if you think about the class, like we spent a lot of time, like, doing numerical calculations, some graphs. Then we spent a lot of time on correlation and regression, and then probability. And then we started learning about probability distributions. But like this stuff here is what's mostly, I don't want to say it's like how statistics is used in the real world, but like advanced statistical concepts, like when we get to confidence intervals and hypothesis testing, they all come from this concept of called sampling distributions. Okay. And we're going to cover 2 types of sampling distributions in the coming weeks. Okay. So today's class is going to be about the sampling distribution of the sample mean. And then next class on Thursday, we'll start the sampling distribution of the sample proportion. And in today's class, and I know I say this all the time, but in today's class, the first 45 minutes of the class are kind of like a theory-based class. Okay. So just stick with it and try to comprehend, kind of keep some of the concept and things I talk about in class in your mind, and, pause and ask questions for clarifications. But then a lot of this stuff gets flushed out when we do our first example, and I know I say that all the time and I always ask for reinforcement, but you guys find that, right? Like when I explain stuff, once you get to the first example, it makes sense. I hope so. Because that's kind of what's going on here today. All right. Yeah, so just bear with me. All right, is everybody okay if I go to start going into the slides here? You guys can all hear me, right? I'm not just talking to myself. Okay, thank you. Thank you. All right. All right, so statistics. Okay, so statistics are values calculated from a sample. So a statistic such as X bar, okay, which is the sample mean, all right, are random variables. Okay, so statistics are random variables. And why is that? Okay, so like imagine if I take a random sample of 30 students and compute their average height, and then take another random sample of 30 students and compute their average height. Do you think those 2 averages of those 2 different samples are going to be exactly the same? What do you think? So should have yeah. Thank you, Bertha. No, they should not be the same. Like it's just 30. The height, the average height of 30 random people should not be the same as the average height of another 30 random people. Okay, so statistics, all right, like X bar, like sample means, their values are going to vary from sample to sample. Okay, it turns out that these statistics, okay, like X bar, have probability distributions associated with them. Okay, so some of the probability distributions we've studied so far in this class, like we've studied the uniform distribution, and we've also studied the normal distribution. Okay, those are the probability distributions we've studied. So in this section or this chapter, what we're going to do is we're going to focus on the shape, center, and spread of a statistic like X bar. Like, all right, we realize that, from sample to sample, the average height of students, keeping with that example, won't always be the same. So like if we did this over and over and over again, what would the distribution look like? All right. Is everybody okay if I go to the next one? Not much here to copy. All right, and so this is the first example I want to illustrate this concept with, okay? So it turns out that the weights of pennies minted after 1982, that was the year I was born, that's cool, are approximately normally distributed. So what this is saying is, do you think every single penny weighs exactly the same weight?
Okay, so I'm sorry, but I can't locate your PowerPoint.
Sure. So yeah, no problem. So this PowerPoint was actually the one from last week.
Oh, okay. I opened the ones for today. Okay.
Yeah, I'm sorry. Yeah. I didn't finish the one from last week.
All right. Thank you.
Yeah, no problem. Yeah, it's still under week 9 here. Yeah, and then later on and during the second half of class, I'll finally move into this one. Yeah, my apologies. Okay. So let's just think about this. Do you think that the weights of pennies are every single penny in the world, weighs exactly the same amount? Like it's like perfect. Like there's a minting process. There's a manufacturing process to making pennies, right? So like there's no way that every penny weighs exactly the same amount. Okay, it just wouldn't happen. So here's what we're saying: that weights of pennies, how much pennies weigh, are approximately normally distributed. So the weights of pennies, the distribution of them follows this bell curve, right, with a mean. So the average penny weighs 2.46 grams. Like this, okay? And I also give you the standard deviation. All right, so they're telling you that the average is 2.46 grams. And the standard deviation for pennies is 0.02 grams. All right, so imagine this. Imagine you, and the next thing it says approximate what we call the sampling distribution of the sample mean by obtaining, and I'm going to explain this, 200 simple random samples of size n is equal 5 from this population. All right, so this is what you're going to do. You're going to sample, the first thing you're going to do is you're going to sample 5 pennies. Okay, and you're going to compute X bar from those. You're going to compute the sample weight. I'm going to call this X bar 1. Then you're going to do this again. You're going to sample another time. You're going to sample another 5 pennies. All right, and you're going to compute that X bar, the average weight of those 5 pennies. And you're going to keep doing this. And it says to do this 200 times, okay? You're very bored on a weekend, and this is what you're going to do. All right, so how many sample means am I computing here? So I'm going to compute 200 sample means. All right, does everybody kind of following me here? What I've done is I have 200 different sample means, and each of those sample means came from a sample size of 5 pennies. All right, does that make sense?
Yes.
Okay. So let me just show you, for example, what the first sample looks like. Okay. Is everybody okay if I go to the next slide? Okay. All right. So the data on the following slide, okay, represent the sample means of the 200 simple random samples of size n is equal to 5. Okay. So on this next slide here, these are the 200 sample means I computed. Okay. So this first one here, this is the first sample I did. Okay. Where's my pen? This is sample 1. And this all the way down here is sample 200. So this first sample mean was 2.479. Okay. So the first 5 pennies I sampled, these were their weights. And if you were to take the sample mean of this, that's where this 2.479 comes from. Okay, but so what did I say? If you look back on the previous slide, what did I say that the mean of all pennies were? Thank you, Alexander. Yeah, 2.46. So is this sample mean of these 5 pennies exactly 2.46, or is it a little higher? What do you guys think? Well, it's a little higher, right? So this sample mean is higher than 2.46. So this mean is higher than the population mean, which is okay. Like, it's just a sample of 5 pennies. It's like not a big deal. All right. So I'm going to go to the next slide for a second. So these are all the 200 sample means. Okay. So these are the 200 sample means from size. Each sample is only 5 pennies. So here's what I want to do. Okay. What I want to do is I want to take this raw data and construct a histogram of it. So here's what I'm going to do. I'm going to construct a histogram of the data. And then what I'm also going to do is I'm going to also find the summary statistics for this. So I'm going to find the summary stats of the 200 sample means. So basically when I say that, what I mean is like, well, what is the average of these 200 averages? And what is the standard deviation of these 200 averages? And something really like super interesting actually happens when you do this. Okay. And is everybody okay if I go to the next slide? I hope so. I hope everyone hasn't zoned me out and is on Facebook or their phones right now. It's okay. Like, I get it, Thank you, Jamie. I appreciate it. Thank you, Storm. I appreciate that. It's okay. I do get it though. You know, my phone is right next to me too, so I understand. All right, so it turns out this is crazy when this happens, but the mean of the 200 sample means is it ended up being 2.46. Okay, so this is what happened. The average of the averages was the same as the population average. And this is one of the key things about statistics that's really important. I just want to like explain this, okay? The whole point of statistics is to be right on average, okay? So when you take these 200 samples, like this sample mean right here, 2.479 was a little bit higher than the real sample mean. This last one, 2.456, was a little bit below the real population mean, excuse me. But if you were to take the average of all these values, the average would be the same as the population average. So you would be right on average. That's what we're seeing here, which is a really, really cool thing in statistics. Now, if I were to take the standard deviation of all these, okay, like if I were to just treat this as a set of data, and I were to take the standard deviation of this, okay, the standard deviation of these 200 sample means would have ended up being this number. So I just went ahead and did it for us. Okay, which is smaller so than the deviation of the population. Okay, so just recall that the population standard deviation was 0.02 grams. Okay, so look, the average was the same. So the average of the 200 sample means was the same, but what was different, what got smaller, was the standard deviation. Okay, and so the next slide shows the histogram of these sample means. So if you were to take these 200 sample means and construct a histogram of them, this is what you would see. Okay. What does this kind of look like? What type of distribution? It's not perfect, but what does it somewhat look like? Starts with an N.
Yeah, normal.
Looks like a normal distribution. Like, it's not perfect, not perfect. The only thing that's perfect in this world is my wife. Okay. So this is not perfect. Okay.
That's a great answer.
I appreciate that. She's not even in the house. Okay. I just love my wife. I can't help it. All right. So this right here, it looks like a normal distribution. I love my son too. He's just a little bit stressful these days. Don't ever, you know what? Unfortunately, this is going to be stuck on the internet forever because I'm recording this. So I'm going to rephrase that. I love my son to death. Okay. He's the greatest thing ever. And I'm just going to leave it at that. I just wish he would not get up every day at 5:30. That's just the only thing I wish was that he would just sleep for another hour. You know what? I realize right now I'm just digging myself into a ditch. So I'm just going to stop. Okay. Anyways, I'm glad you find that funny. So this is what we're seeing here is this looks like a normal distribution. So this, okay, this is what we're seeing here. This is called the sampling distribution of the sample mean. And if you look here, what's really cool is the high point of this graph ends up being the same as the population mean. Okay. So what this is saying is, look, when you take a sample, most of the time when you take a random sample, the mean of your random sample is going to be pretty close to the actual mean. Sometime you're going to sample, but not that often, and your mean is going to be way high. And sometimes you're going to sample and your mean's going to be way low, but the majority of the time you're going to be centered right around the real population mean. Your statistics should be close to this real value. All right, so it turns out that this sampling distribution of the sample mean, it turns out it looks like a normal distribution. All right, so let me expand on this before I want to cover some major topics before we get to our break. So I'm going to move on to the next slide here. So what role does n, the sample size, play in the standard deviation of the sample mean? Well, let me ask you this, and this is kind of just a thought process, right? Are larger sample sizes better? Like if you were a statistician, would you want to collect as much data as possible, or is like, 5 pennies, a small sample size, okay? What do you guys think? In statistics, is the larger the sample size better or no?
No.
The larger would be.
Well, so think about this, and I know it's the way I'm saying it, and the inflection in my voice makes it sound like a trick question, but would you guys agree that the more data you have, the better? Like in the real world, you want to collect as much data as possible. Okay, so like for example, if I wanted to take a survey of college students or something, like a survey of 1,000 college students, those results are probably more accurate than a survey of 10 college students. You see what I mean there? So yes, okay, larger sample sizes. So it turns out actually smaller does not mean more accurate in this case. Like the more data you have, the better. Like it's just the more data you collect, the more accurate you get. So like when I say better, what I mean is it's more accurate. Okay, so like if you're going to take, one thing away from class today, right? Like take away that, larger sample sizes are more accurate. So now here's what we noticed, and I'm just going to go back for a second, that the standard deviation of this distribution so the standard deviation of this histogram was 0.086. Okay. So what we saw here was when we increased the sample size, okay, we went from, just, and I didn't mean to say increase the sample size, but when we took a sample size of 5, the standard deviation of this distribution was way lower than the standard deviation of all pennies. So what happens is, as the size of the sample increases, the standard deviation of the distribution of the sample mean decreases. Okay. What this means here, okay, is as you increase the sample size, your statistics, which are X bar, become more accurate. So this, you're going to hear me call this something else later on, but the standard deviation of a sampling distribution is also referred to as what's called the standard error. Okay, so if you think about what a standard deviation is, a standard deviation is the average deviation from a mean. So like if you were to take, this is the average of all the averages, okay? And so this average here, 2.479, is not exactly equal to 2.446, which is the population mean. So it made a little bit of an error. It was off. So we call the standard deviation of these distributions the standard error. And so if you were to repeat this, okay, so if you were to redo this experiment, okay, of collecting 200 random samples, but this time of size n is equal to 20. So you're increasing the sample size from n is equal to 5 to n is equal to 20, okay? Let me ask you this. What do you think will happen to the standard deviation? Okay, so original population standard deviation was 0.02. When I took a sample size of 5, the standard deviation got smaller to 0.0086. So now I'm doing a sample size of 20. Do you think the standard deviation is going to continue to get smaller or larger? Well, watch what happened when you went to 5, the standard deviation got smaller, right? So what's going to end up happening, you'll see, and it was a good guess, it should shrink. It should get smaller. So watch, let me show you this. Yeah, exactly, Storm. Yep. If you look here, right? So now this histogram shows the sampling distribution of the sample mean. And this is when each sample is 200, okay? When you look at this distribution, what does this one look a lot more like? Starts with an N.
Normal.
Yeah, it looks like a normal distribution. And this is crazy, right? This is amazing, actually. If you were to take the average of these 200 sample means, again, the average, this curve is centered around 2.46. Okay, so notice that the mean when n was equal to 5 was still 2.46. Okay, the standard deviation, though, was 0.0086. Now, the mean here when you have a sample size of 20 was also 2.46. So notice it's the same, but the standard deviation of this distribution had actually ended up getting even smaller. The standard deviation was this now, okay, 0.0045. So it looks like as you increase the sample size, standard deviation got smaller. And the reason is as you increase the sample size, your sample means become more accurate and there's less variability between them because they're becoming more and more accurate. Smaller sample sizes, less accuracy, more variability. Larger sample sizes, more accurate, less variability. Okay, but what you're seeing here, okay, and what's important here is that, again, you're seeing a normal distribution. Okay, so it turns out that statistics like X bars, like sample means, have their own distribution. And it turns out, and this is what's awesome, that statistics like X bar, like these sample means, are going to be normally distributed. They're going to follow the bell curve shape. All right, is everybody okay if I go to the next slide?
Professor, can you go back on the previous slide for a second?
Yeah. You want me to go back to this slide right here? Is this the one you wanted? If you're trying to talk, you're on mute.
Oh, the next previous, I'm sorry. Yes.
Yep, no problem.
Okay, thank you. It's good. Thank you.
You're good?
Yes,
Okay.
I'm good, Professor. I'm good.
Okay, thanks. All right, so this slide right here is going to be the most important slide for how we do these application problems, okay? And it says this is what's called the mean and standard deviation of the sampling distribution of X bar. So this is what I've been trying to hit home, okay? These X bars, okay, are a random variable, and the distribution of these random variables of these statistics is normally distributed, okay? Didn't matter in this case, and I'll explain the nuance here, but in this case, it didn't matter if it was sample size of 5 or sample size of 20, okay? Because the original population was normally distributed, these bell curves, the distribution of the sample means is also normally distributed. So when something is normally distributed, okay? All right, since the sampling distribution of X bar is normally distributed, it means we can find the mean of that distribution and the standard deviation of that distribution. Okay, that's incredibly important. Whenever I tell you something is normally distributed, you're going to tell me what the mean and what the standard deviation is. All right, so it goes like this. Suppose that a simple random sample of size n is drawn from a large population, okay? And this large population has a mean mu, okay? Like in the case of the pennies, it's 2.46, and it has a population standard deviation sigma, okay? Like the weights of the pennies were, the standard deviation for the weights of pennies was 0.02 grams. Then we can say the sampling distribution of X bar will have mean. So we denote this as mu sub X bar, okay? So think of it as the average of the averages. It's always equal to the population mean, okay? So your statistics on average will be the same as the population average. And the standard deviation is actually incredibly easy to calculate. Okay, we denote it as sigma with the subscripted X bar. So this tells me it's the standard deviation of the averages of the sample means. And all you do is you take whatever the population standard deviation is and divide it by the square root of n. Okay, so as n gets larger, you can see that this value shrinks. Okay. So this is why the standard deviation got smaller as you increase the sample size. All right, and so what we do here is we say that the standard deviation of the sampling distribution of X bar, which is a big mouthful, we actually just call this the standard error of the mean, okay? And that's denoted as sigma X bar. All right. I know it's a little confusing, but trust me, as you see the first example, it won't be too bad. Is everybody okay if I go to the next slide here? Okay. All right, so this is what we saw. I said the weights of pennies was normally distributed, okay? So if a random variable X, like the weight of a penny, okay, the sampling distribution of X bar, so the distribution of the sample means is normally distributed, no matter what the sample size is. Okay, and that's what we saw in this previous example. Like, it didn't matter if the sample size was 5 or 20. Okay. So if I tell you in the problem that X is normally distributed, then the sampling distribution of the sample mean is also normally distributed. Always, always, always. So it goes like this, okay? And the what I have here, this thing called the central limit theorem, is like the most important theorem of the class. Like, if you were to remember, if you're going to remember like one thing from this class, okay, you should obviously remember that my jokes were pretty funny. But if you're going to remember two things from this class, you should remember thank you for the laugh there. You should remember the central limit theorem, because it's it comes up the most in advanced study. Okay. All right. So the mean of the sampling distribution is equal to the mean of the parent population always. And the standard deviation of the sampling distribution of the sample mean is always sigma divided by the square root of n. All right. So the central limit theorem tells us this. The shape of the distribution of the sample mean becomes approximately normal as the sample size n increases, regardless of the shape of the population. So it turns out that as long as n is greater than or equal to 30, that's the magic number, the sampling distribution of X bar will be normal. Always. So as long as you have sample size greater than 30. All right. I just, before we go to break, I just want to do I just want to cover one last thing, and then we'll go take our break, and then we'll come back from break, and then we'll do just application problems for the rest of the class, so you can understand how we're going to use this. Okay. So just bear with me on this. Okay. And this next part is really, really important. It's talking about this central limit theorem. Okay. So in the previous slides, what happened was I said, look, weights of pennies are normally distributed. So it turns out that the average of random samples is normally distributed. Okay. But what if like the population is not normally distributed? All right. So I'm sorry. I just want to do a sports example for a second. All right. What major league sport is starting on Thursday? Does anybody know?
Baseball.
Oh man, yes, I love baseball. Okay. Are there any other baseball fans in here? I'm just curious.
Yankees all day. Let's go.
Yankees would be good, except their players always get hurt, right? So I guess there's one other baseball fan. Are there any other baseball fans in here? No, but nobody else is a baseball fan. Alexandra, that's great. Got one other baseball fan. So anyways, well, let me just say this. I am a huge baseball fan. I follow baseball like crazy. I play fantasy baseball with my best friends. Like I just love baseball. All right. So I want to do this kind of baseball example. And what I want to talk about, you don't really need to know like much about baseball. All right. But what I want to talk about is baseball player salaries. Okay. So I'm going to fudge the numbers just a little bit, okay? Just to make things easier. If you're a Major League Baseball player and you make the major leagues, there's a minimum salary that you're paid as a Major League Baseball player, okay? Does anybody have a guess what the league, they call it the league minimum salary is in baseball?
I'll take an estimate guess of 12 million.
That is not the league minimum. That would be something, but it's a lot less than that actually. So the league minimum, I'll help you guys out. The league minimum is around $500,000 a year. Okay. So what that means is like the backup catcher on the team. Okay. Who's like just out of the minors, that they make the league minimum. Okay. This year, does anybody know who the highest paid player is? I'm just curious. Does anybody have a guess who the highest paid baseball player is?
Plays on the Washington. He used to play on Wash. What's his name? Oh gosh.
Are you thinking Bryce Harper?
Yes, I am.
Bryce Harper is not the highest paid player in baseball.
You think of a pitcher?
It is a pitcher.
Played for Houston, right?
No. I'll help you guys out. So the highest paid player this year, just on yearly salary, not total contract. The highest paid player this year is somebody named Trevor Bauer. I'm just curious. Has anybody ever heard of this guy?
Not really.
Trevor Bauer, he's this pitcher on the Dodgers, and he's making $40 million this year. Okay, just for this 1 year of baseball, he's getting paid $40 million. Is that pretty good salary? Yeah, you know what I would do? I would play 1 year of baseball, and then I think I'd quit. Okay. It is a lot of money. Yeah, I don't know if he's worth it or not. Okay. I don't know. I'm not here to comment on that, but I do like the guy. He's actually really funny. But anyways, so the average salary in baseball, do you think most players make what Trevor Bauer makes, or do you think most players make closer to the league minimum? Well, let me help you out here. Most players make, closer to league minimum. There's actually a couple teams in baseball whose entire payroll of their entire team is less than what Trevor Bauer is making this year. Like the Pittsburgh Pirates, I think the Tampa Bay Buccaneers are pretty close, or Tampa Bay Rays. They're pretty close down there. So the average salary is roughly $5 million. Okay. But if you were to look at the distribution of baseball player salaries, here's what the distribution would look like. All right. Here's the league minimum, $500K. Here's the average, $5 million. And here's what Trevor Bauer makes, $40 million. The distribution of baseball player salaries look like this. Okay. Does that look like a normal distribution or something else?
Something else.
Yeah, this is what's called a right skewed. Now, baseball players are paid quite a bit, but the majority of baseball players don't make what Trevor Bauer makes. Okay. They make closer to the league minimum. Each team has a couple players that are maybe making a couple million, and then they got a couple $5, $10, $15 million players, maybe. And then only these big market teams like the Yankees and the Dodgers can afford to pay these huge salaries. All right. Anyways, so what's really cool is if you did this, suppose you took $200 random samples of size 30. And the reason I picked 30 is, look, this is a non-normal distribution. The central limit theorem says as long as you have a sample size of at least 30, the distribution of your averages, your X bars, will be normal. And so I've actually done this experiment. Back when I was an undergrad myself, I did this. It's very easy. So what you're going to do is, you could write a computer program to do this. Okay. So you take 200 random samples, each of size 30 from all the baseball players. And you look at the distribution of X bar. Okay. And what is X bar? It's the sample mean salary of the 30 players. And when you look at the distribution, here's what's crazy. Okay. So the league minimum, the league average was around $5 million. Suppose the first time you sample 30 baseball players, you get a sample mean that's a little bit higher than 5 million. The next time you do it, you get a sample mean that's a lot lower. And you keep doing this. If you were to do this 200 times, in each of these asterisks represent a different sample mean. This is what your 200 sample means would end up producing. And hopefully you can see what I'm getting towards here. If you were to look at this, what does this shape look like? Pyramid scheme, but like not a pyramid scheme, but starts with an N.
Normal distribution.
Yeah, so even though baseball player salaries are not normally distributed, if you were to take random samples of size 30, at least 30, and compute their sample means, that distribution of those sample means would be normal, and they would be centered around the population mean, which is really wild. Okay, so this distribution works, or this concept works, even when your population is not normal. And the reason we care about that, is we know how to work application problems for a normal distribution. So if you have a population like baseball player salaries that are not normal, you could just take a random sample of size 30, compute that mean from that size 30, and that mean will be a random variable that is normally distributed. And it turns out there's a ton of amazing applications so you can work from it in this class. And that's what we're going to spend the next 6 weeks talking about. All right. Let's, how about we take a 10-minute break? What do you say? Because we've been going for about an hour. All right. And what I'm going to do when we get back from our break is I'm going to switch to the other PowerPoint from the one that's in our classroom under week 10. I'm going to do this lecture right here. Okay. So we're going to start that today. All right. Does anybody, so it's 1:58. We'll come back around 2:08. So we'll take a 10-minute break. All right, no questions. I'll go enjoy a break. Okay.
Time goes really fast with statistics. It's like every minute is interesting.
I'm glad to hear that. All right, I'll see you guys back in 10 minutes. All right. Can everybody hear me okay?
Crystal clear.
All right, good. So all I want to do during the second part of class here today is I just want to start doing application problems to this sampling distribution, the sample mean, okay? And I just want to get through two examples here. So if you don't have your graphing calculator, take that out now. We're going to use it a bunch. And ultimately you're going to see that, these problems are almost identical to the problems we were doing last week on Thursday with our graphing calculator, just with an extra step. Okay. All right. So this is kind of just a review from the first part. Okay. So the sampling distribution of X bar will have mean mu sub X bar is equal to mu, and it will have what we call standard error, which is the standard deviation sigma X bar. You're going to take the population standard deviation and divide it by the square root of n. Okay. And the central limit theorem, all right, tells us, look, as long as n is greater than or equal to 30, your sample size is greater than or equal to 30, your distribution of your sample means will be normally distributed. Okay. So here's the first problem. Okay. Suppose that the mean time for an oil change at the place, and it calls itself a 10-minute oil change joint, is actually 11.4 minutes. Okay, so is it really a 10-minute oil change joint? No. Okay, so what we're saying here is, look, the average time to get an oil change at this place called 10-minute oil change is actually 11.4 minutes. And the standard deviation for how long it takes to get an oil change is 3.2 minutes. Okay. Now look at the problem. Do I say anywhere in the problem that the time to get an oil change at this place is normally distributed? Do I say that anywhere in here?
No, you do not.
I do not. Okay. So look. So time for an oil change is not normally distributed. It's not listed. Okay. It is not listed anywhere. So here's what you're going to do. If a random sample of n is equal to 35 oil changes selected, describe what we call the sampling distribution of the sample mean. And what the sample mean here is going to be is, look, I'm going to randomly sample 35 oil changes at this company, and I'm going to compute the average time it takes them to get an oil change. Okay. So now here's the thing. Before I take this sample mean, okay, am I going to know what the average of these 35 oil changes is going to be? Like, it's just a random sample of 35 oil changes, right? Like, it's just going to be some random value. It's going to be some random outcome. So here's what I'm going to start by doing. I'm going to start by defining a variable. I'm going to let X bar, okay, be the sample mean, oil change time for a random sample of 35 oil changes. All right, so now here's the thing. It says describe the sampling distribution of the sample mean. All right, so what did I just spend the last hour of class saying? The distribution of X bar ends up being what? Starts with an N. Starts with an N. Go on ahead. Anybody?
Normal.
Yeah. So here's the thing. It's going to be, yep, Jamie, you got it. Thank you. Thank you, everybody. But here's the thing. Certain requirements need to be met. Either the original population needs to be normally distributed, which it is not. And what does the central limit theorem say the sample size has to be greater than? It just has to be greater than, what was the magic number I said?
30.
Yep. And is this number 35 greater than 30? Yes. Yeah. So here's what's going on. When I say describe the sampling distribution, what I'm really always going to want you to do is verify, tell me why it's normally distributed. And find the mean and standard error. All right, so this question is going to be answered something like this. Since the sample size is greater than or equal to 30, okay, it is 35, we can say the sampling distribution of X bar, okay, these 35 oil changes is normally distributed with a mean, which we denote as mu sub X bar, so the average of the averages. And if you look back here, it says the average of the averages is equal to the population average, mu. Well, what is the population mean here? What is the average time for an oil change at this place?
$11.4.
Yeah. So look, this is what this is saying. Look, when you take an average of 35 oil changes and compute, or you take a sample of 35 oil changes and compute the average time it takes for those oil changes to happen, on average, the average of all your averages should be 11.4. And when something's normally distributed, you give the mean and standard deviation, which is called the standard error. And all that is, it's sigma sub X bar. And all you're going to do is take the population standard deviation and divide it by the square root of the sample size. So look, sigma is 3.2 minutes. And I'm going to divide it by the square root of what? What number?
$35.
That's it. So grab your trusty calculator. You're going to take 3.2 divided by the square root of 35. And if you follow along, you should get something like this. Okay. And when you do this, take a number like this out a couple decimal places. So I'm just going to go out 4 decimal places here. So it's 0.5409, 0.5409. So look, here's what's going to happen. We've now described the sampling distribution. We've told you it's normally distributed with a mean, and the standard error is what's called the standard deviation is called the standard error here. So normally distributed, mean, and standard deviation. Now I'm going to ask you a probability, which is exactly what we were doing last week. Okay, the only difference is, the only new thing really this week in terms of calculations is this right here. So the next problem says this. If a random sample of sample size n is equal to 35 oil changes is selected, what is the probability the mean oil change time is less than 10 minutes? So look, this is the mean. This is the sample mean. So this problem is, what's the probability that X bar, our sample mean, is less than 10 minutes? Well, you know what's great? X bar is normally distributed, mean, standard deviation, and I ask you for a probability. You can use the normal CDF in your calculator. Which is like amazing, okay? You might ask yourself, how? Why can we do this? When somebody asked me to do a homework problem, what did I say was the most important thing to do? Like, what helps me solve this?
Draw the curve.
Draw the curve. And here's why we're going to draw the curve. Maybe you look at this and you're like, Matt, I have no idea how to answer this. Well, X bar, the probability distribution is normally distributed. So you're going to sketch the curve. What is the average of this curve? Right here, 11.4. And I want to be less than 10. So 10 is over here, and I'm going to shade to the left. Whenever in this class you draw the normal curve and shade in an area, you can use the normal CDF. Okay. All right, so what is the first thing that you have to put in the normal CDF? It's the lower value. Well, I have a left-tailed test or left-tailed probability here. Does anybody know what number I put in?
-999.
That's correct. Comma, then your upper. Well, what is my upper value? Where does the red area stop at? What number?
10.
Yeah. And then what goes in there is the mean. Next. Well, guess what? Boom, mean right here. That's why we've said, what is the sampling distribution? So mu sub X bar, well, that's 11.4. And now this is really important. What goes next is the standard deviation. Okay. But what we're plugging in here is the distribution of X bar. All right. So what is our new standard deviation in this case? Do I plug in 3.2 or do I plug in something else?
Plug in something else.
Okay. And look, the standard deviation, the new standard deviation we call the standard error is this number here, 0.5409. So look, I'm going to break things down just a little bit. Do you really, whenever I ask you a problem about the probability that a sample mean is less than or greater than or something like that, really the only new calculation you did here was you took the population standard deviation and you divided it by the square root of n. That was it. So you never plug in, you like never plug in new, I'm sorry, I got a little sidetracked there. The only new thing you're going to plug in is this new standard error you calculated. For these problems with the mean, you're never going to plug in this 3.2. You're always going to have to divide it by the square root of the sample size. And then once you do that, we can find this problem. So normal CDF, negative 99999, comma 10, comma 11.4, comma 0.5409. And this is your answer right here. So it's 0.0048. So it's really small. So look, I spent the last hour of class trying to tell you that whenever you have these problems involve the probability around a sample mean, if the theory was super confusing, like just for these problems, you just need to divide by the square root of the sample size for the standard deviation. That's it. All right, everybody ready to see continue on with this problem?
Yep.
Okay. So look, I'm going to continue this. Suppose that the mean time again for the oil change is 11.4 minutes and the standard deviation is 3.2. Okay, fine. Now again, if a random sample of 35 oil changes is selected, what is the probability that that sample mean, that the mean oil change, so it's the probability that X bar is greater than 12 minutes? All right, don't worry. I'm only going to ask this a few more times. What do you think the key to solving this problem is?
Sketch.
Sketch the curve. People are probably going to be sick of hearing me say that. Well, how is the sample mean distributed? Well, we learn it's normally distributed. The average is still 11.4 minutes. And I want to be greater than 12. So I'm going to shade then to the right. Okay. So when I shade in the curve, when I draw the curve and shade in some area, you're always going to use the normal CDF to answer this probability. So the lower value goes in. Right? In this case, because it's a right-tailed probability, what is the lower value?
12.
Mm-hmm. What is the upper?
99999.
99999. Next goes the mean, which is what? $11.4. And now notice the difference. Here I'm asking the probability that X bar is greater than 12. So what is the standard deviation I will put in? Will I put in 3.2 or something else?
That'll be the something else.
Yeah, you put in that 0. I think it was 5409.
Yes.
Yep. So let's do that. Normal CDF. You're going to go 12, comma, 99999, comma, 11.4, comma, 0.5409. And if you're following along, how many people got this on their calculator?
I'm with you.
That's it, 0.1337. Okay. All right, I want to do D, and then I just want to get, yeah, let's do D, and then we'll start the next one, okay? So if a random sample, again, of N is equal to 35 oil change is selected, what is the probability now that the mean is between 10 and 12? There's a probability that the mean is between 10 and 12. So again, you can sketch this. Average is 11.4. I want to be between 10 and 12. So again, this will just be normal CDF. What's my lower here?
Excuse me.
What's the lower value I'm going to plug into my normal CDF here?
10.
10.
What's the upper?
12.
Okay. The mean is 11.4, and because it's a probability with X bar, you're going to need this new standard deviation, 0.5409. So normal CDF, 10, comma 12, comma 11.4, comma 0.5409. And this is your answer, 0.8615, 0.8615. All right, what do you guys think? Do you find like the hardest thing is just really understanding what's being asked? Like once you, like none of the calculations with the calculator seem too hard, right? Like it's always just figuring out what information to glean from the problem, I think is the hard part. Or how to take the information that's given in the problem and plug it into your calculator. I think that's the hardest part. You guys agree?
I agree with both statements.
Thank you. Okay. All right, let's just do the first two parts of the next problem, and then we'll call it quits for today. Okay. All right, so it turns out, and I think I've done a problem like this before. The length of human pregnancies is approximately normally distributed. Okay, so right off the bat, I'm telling you it's normally distributed. So what that means is you don't need the sample size to be greater than or equal to 30. Okay, you don't need that anymore. It's just if the underlying population, like human pregnancies, is normally distributed, then the sample means will be normally distributed. All right, so with a mean of, so they're telling you that the average is 266 days and the standard deviation is 16 days. All right, so here's the problem. What is the probability that a random sample here of 16 pregnancies has a mean length greater than 270 days? Okay. So I'm going to take a random sample of how many pregnancies? What does the problem say? How many pregnancies?
16.
Yep. And here's what I'm going to do. I'm going to take 16 random pregnancies, and then I'm going to compute the average length of that pregnancy, of those 16 pregnancies. And then I want to find the probability that that mean is greater than 270 days. So here's how you're going to solve this problem. You're going to start by defining a variable. I want to find a mean. So I'm going to let X bar be the sample mean length of 16 pregnancies. And look, here's the thing. Because the underlying population is normally distributed, the distribution of X bar will be normally distributed. And whenever you're told something is normally distributed, all right, you want to find the mean, which we denote as mu sub X bar. And mu sub X bar, so the average of the averages, is the same as the population average, which is 266. And the standard deviation, we call the standard error, sigma X bar. What was the formula for that?
O divided by square root of n.
Yeah, it was sigma. Yep.
Sigma. Yeah. Okay.
Yeah. So in this case, sigma is 16 days divided by the square root of 16. Well, square root of 16 is 4. 16 divided by 4 is 4. So now here's the question. I wanted to find the probability that X bar is greater than 270. Well, you can see how this goes. You sketch the curve. The sample means are normally distributed. You're centered around 266. And I want to be greater than 270. And 270 is over here. And I'm going to shade to the right because I want to be greater than. Well, whenever you shade in a curve, normal curve, what do you use in your calculator?
Normal CDF.
Boom, normal CDF. So the lower value here is 270. The upper, because I'm shading to the right, is 99999. The mean is 266. And now what standard deviation are you going to plug in? Is it 16 or 4?
4.
You plug in 4. Yeah, you plug in 4. Grab the trusty calculator. Normal CDF. 270, comma 99999, comma 266, comma 4. And the answer to this problem is 0.1587 when I round it. 0.1587. Okay, so basically, do you see that the extra step here is you're just taking the standard deviation and dividing it by the square root of the sample size? Do you guys notice that this is really the only thing different than what we were doing last week? Literally the only difference.
Slightly.
Slightly, yeah, only different. Slightly, yeah. I guess we're probabilities involving an X bar, but like ultimately, like to get the right answer, just make sure you divide the standard deviation by the square root of the sample size. All right, we'll just do this one here. What is the probability now that a random sample of 20 pregnancies? So it's not 16 anymore, it's 20, has a mean length greater than 270 days. Well, let me ask you this. Now it's going to be 20 pregnancies, not 16. Are any of our numbers going to change? Does anything change?
No.
The standard deviation,
Yes. Why does the standard deviation change? You're right.
because the bigger number, the standard deviation will be smaller.
Yeah. No, look, our standard deviation is a function of the sample size. So if the sample size was 16 and now it's 20, this n is going to change this formula right here. So you have to pay a lot of close attention to that. So I'm going to now let X bar equal be the sample mean length of 20 pregnancies now. We know X bar is normally distributed. Mu sub X bar is equal to still 266. That's not going to change. That never changed. But this changes. Sigma X bar. You're going to take 16 and now you're going to divide it by the square root of 20. So that changes. And my new standard error, my new standard deviation got smaller. Okay. It's not 4 anymore. It's 3.5777. Really, really important that you pay attention to that. So now the probability that this sample mean, this new sample mean is greater than 270, it's going to be almost the same. It's still going to be normal CDF. It's going to start at 270. The curve would be the same. Go into 9999999. I think I had an extra 9 in there. 266. But now instead of plugging in 4, I'm going to have to plug in 3.5777. So you just have to pay real close attention to that. And the probability you're going to notice is going to change. It was 0.15. Yes, the private question that was messaged to me, yes, n is always equal to whatever the sample size is in the problem. Like it will always be given to you. Yes. So this one looks like it's 0.1318 when I round it to 4 decimal places. All right, I know there was a lot to cover in today's class and a new concept, and don't stress. We're gonna just do more examples next class. Okay, that's all we're gonna do on Thursday. More examples, more examples. Okay. So the next class, what we're gonna do is I'm gonna end class little 5-10 minutes early here. Next class, what we're gonna do is we're gonna spend the first hour just doing more examples of this stuff right here. Maybe the first half an hour, and then during the second part of class, we're going to talk about the sampling distribution of the sample proportion. All right, so let me stop the recording.